Now that geothermal has finally started to catch on, there comes a need for more training and experimentation with these systems. That's where OIT, the Oregon Institute of Technology, has really taken a leadership role. For our community spotlight this month, we traveled to Klamath Falls in southern Oregon to see Oregon's first geothermal power plant right there on the OIT campus and to find out what OIT is doing to help create the next generation of geothermal engineers. Let's take a look.
Hello and welcome to Sustainable Today. We're here out in front of the first geothermal power plant in Oregon, and we're here talking with David Epson, Director of Facilities here at OIT. David, can you tell us a little bit about this facility?
I sure can. OIT sits at the far north end of a geothermal plume that sits under Klamath Falls. The hotter wells are more towards the center of town. We're at the far north end. We have 192 to 195 degree water. The city has over 200 degree water. In order to determine where we drill our wells, we did a seismic survey where we, on two different axes, drilled a series of holes and set off dynamite charges in each one of those holes. The sounding from that was recorded. We take those soundings, we look at where the fault lines are, and we locate our wells, both our production wells and our reinjection wells, based on that geology and the flow and direction of the groundwater resource. We're running 3 wells. We have a variety of wells that produce different volumes. Our small well, which is behind us here, well number 2, is drilled to a depth of about 1,200 feet. Well number 5, which is our big well, produces about 450 gallons a minute. It's drilled to about 1,600 feet. And then well number 6 is drilled to about 1,800 feet deep. Our largest drilled well, which was drilled in February of 2009, is over a mile deep, and it produces a little over 2,500 gallons a minute of 194 degree water. These are the actual pumps that are at the bottom of the well column. The perforations you see are where the water is inlet, and above that is the bowl assembly. The shaft is turned by that motor we looked at earlier, and that drives the impellers which are in this bowl assembly. That actually elevates the water, brings the water from the aquifer up to the surface level. What you're looking at here is where our geothermal fluids come from our 3 wells. This is the inlet point for the fluids as they come into our heat exchange building. From here, they go to the power plant or to district heating, whichever the demand need implies. Water comes through here. Our water temperatures right now are running 194 degrees. Since water doesn't boil until 212 degrees, and we're below that with our operating temperatures, we use a secondary fluid. In this case, it's isobutane. This is called a binary plant. It uses a secondary fluid to turn the turbine rather than a primary system, which would use dry steam. If we were able to use dry steam, we would be far more efficient because all we would have would be the hot water, and we wouldn't have to go through the process of recondensing the fluid. So a binary plant runs off of a secondary fluid that boils at a lower temperature, and therefore we are able to turn the turbine with the steam. It's just not water steam.
From the heat exchangers, where do we go next?
Well, this is it. This is the heart of the whole power generation facility. This is the turbine. This unit here is where we run the isobutane in its gaseous state. That turns the turbine and therefore creates electricity. From there it goes back into the system and is recondensed through the cooling towers, and the process is repeated. What we're looking at is the cooling tower water, which is a domestic water, drinking water, that is used to cool the secondary isobutane back to a liquid state before it is reheated again and sent back through the turbine to create electricity again. The water is used through a number of cycles, and when the conductivity is low enough, then we have enough solids in the water, that water goes to a sump, and clean water is reintroduced so that we keep a clean domestic water system to cool that secondary fluid. This is our metering panel. It shows how much power we're generating with the facility, and what it's monitoring right now is the net power that we're producing at 220 kilowatts.
So David, this is a self-sustaining system?
Well, it is in the sense that it generates more power than the pumps demand, but it still needs an exciter load from the utility, which is Pacific Power. But yes, technically it is a little perpetual motion machine. It generates enough power to operate itself. This is a graphic representation of how the power plant is operating. This was developed as part of our digital controls so that everything is operated from a workstation either here or across campus at the Facility Services Building. We are able to control, monitor, and operate all of the campus geothermal power generation and geothermal district heating needs from these workstations. What you see here are the 3 geothermal wells. We know that well 2 is off. We can see that right now we're producing 347.5 gallons a minute of 194 degree from well number 5. We're producing 197 degree water from well number 6 at 289.6 gallons per minute. So that's our operating fluid. That's what's coming into the plant. So we're starting at 194 degrees, we're ending up at 162 degrees. We're using it for our students in the Oregon Renewable Energy Center for their research program, so they have a better understanding of what opportunities they have in the area of geothermal and direct digital control.
We're going to look at this when we look at some of these power plants, is they follow curves like this, and we'll find that there's an optimal point in here, okay? I'm Jamie Zippe. I'm Program Director of Renewable Energy Engineering Program on campus, and we've been running the program now since about 2005. Started it up in Portland. We started it down here in 2007, and we're going to have our first graduating class this year. At the time, there was no baccalaureate degrees in this at all, so we decided it's a gamble, but it seems like a very, very good gamble, given what was going on at the time with the energy situation. We got a lot of inputs from industry in the region. They said we need people who are engineering graduates. They're going to need to take the fundamentals of engineering and become professional engineers to work in this type of career. The first 2 years, you're building up math science, engineering, then you start to specialize in your junior and senior year. And we thought about this and we said, you know, we want to have you guys pick what areas you want to go to. So we have electives in hydroelectric, we have wind power, electrical vehicles, biofuels, solar thermal, geothermal. One thing we're real fortunate with, particularly with the geothermal on campus. We've got a small power plant online already. They actually get some hands-on with this. We've been working on some DOE grants where hopefully we're going to get more ties between the program and the geothermal wells. Last year we had the well drilling operation going on. And this turned into a real gold mine again for the students, because how many students actually get to see a well being drilled in progress, okay? And the Geo Heat Center arranged tours for them. They took them up there. So now when we talk about this in a class, and I'm talking about the mud, or what happens to it, they've actually seen it.
I got to see the instrumentational panel personally, so it felt like a really good moment. We also got a chance to speak with the geologist on site.
So that's, to me, that was super cool, because there's not a lot of other campuses in the world where the students can actually go and interact directly with direct use geothermal and geothermal power generation.
So David, the water has come up out of the ground. It's gone through our power plant, through the school, heating it. What happens to all this water afterwards?
Well, early in the 1990s, it was decided that surface dumping of all of these waters was not a good idea. So we are required to re-inject every gallon that we pump out of the ground. After we create electricity or generate electricity with it, after we provide for our space heating needs, after we heat our domestic hot water and heat some of our sidewalks, we come with our geothermal fluid to one of 2 re-injection wells. This is re-injection well number 1. Just to our east, we have re-injection well number 2. And every gallon that we pump out of the ground goes right back in so that we do not deplete the aquifer and we can continue to use this resource for an indefinite period.
Well, David, I wanted to thank you for walking us through your geothermal facility today. I really appreciate it.
You're welcome.
And I'm Kevin McBride at OIT, bringing you the tools to be sustainable today.